Greetings once again and welcome to my new calculus channel. My name is John Gabriel and today I'll be discussing the proposition 12 of book 2 in Euclid's Elements. So let's begin. Now the statement says that in any obtuse triangles, the square on the sides subtending the obtuse angle is greater than the sum of the squares on the sides containing the obtuse angle by twice the rectangle contained by one of the sides around the obtuse angle to which a perpendicular line falls, and the line cut off outside the triangle by the perpendicular towards the obtuse angle. Okay, so what it's basically saying is this, that well, this actually is an enhancement of what it says. I'm not dealing directly with the actual proposition, but rather because the actual proposition isn't that remarkable. What came from it is more useful and more remarkable and has been around for many, many centuries. So before I discuss this proposition, I just want to quickly say something about trigonometric ratios, okay? So trigonometric ratios are a special non-unique measure of angles. And what I mean by that, well, unlike Wilberger's rational trigonometry, which is a bunch of rubbish, the unique measure of an angle, any angle, say theta, is given by the ratio arc length to the radius. So theta is not equal to arc length divided by radius, because these two magnitudes may not have a common divisor, in which case it cannot be written as a number, which is a fraction. Okay. However, the measure of an angle theta is this ratio, the comparison of the arc length to the radius. So ratios such as sine, cosine, tangent, etc. are measures that do not use arc length and are not always unique. And so these measures use only the shortest distances that are part of a right-angled triangle. In other words, the ancient Greeks used these because it was easier than calculating arc length. And as we know today, we use the methods of calculus to calculate arc length. Okay? In other words, products of arithmetic means. So let's leave that for the time being and come back to the demonstration. So this proposition was realized at first by Pythagoras' theorem, which is this, right? In other words, the square on the hypotenuse is equal to the sum of the two squares. But what happens if, for example, we change the two sides, leaving the hypotenuse the same? So the square on the hypotenuse remains 20, but as this side here changes and moves towards this point here, as A moves towards this point here, this area becomes bigger and the green area becomes smaller, right? Do you see that? Until finally you have that, which is not possible because it doesn't have an angle BAC. So some would say that the Pythagorean theorem is a special case of the cosine formula, but although that might be true, it wouldn't have been realized without the Pythagorean theorem and this particular proposition, which I'm actually not dealing directly with what the proposition said, but this gave rise to the ideas. Okay, so what you're looking at here is a demonstration of the cosine formula and how it works. Okay. And the explanation is simple. You start off with Pythagoras on BDC, right? And you know that BC does not change while AB and AC do change. So the trick is to rewrite both of them in terms of, or to rewrite both of them DC and the others in terms of AC and AB. And when you do that, what you finally have is the difference, which is given by this particular expression here, BC squared minus AC squared plus AB squared. Remember, these two are changing, but this one isn't. And so when you do the calculation, you'll see eventually that this 2ABAC cos BAC is the difference. Okay, and that's all there is to the cosine formula. By going over this, you should be able to understand the cosine rules. So that's probably the most important part of book 2. And there's one, I think there are a couple more propositions, but they're not really that interesting or remarkable. And so I'm going to be completing my presentations on Euclid book 2, and the next time I come back to Euclid, I'll be starting on something in book 3, which is remarkable. Okay, so I hope you've enjoyed this little presentation. You can access the link and to this applet so that you can study it in the detail section. And I've also given you 3 main links, which if you are granted access, you'll have access not only to this applet, but to hundreds of other applets and articles, and also my LinkedIn articles, which were banned from LinkedIn. Okay, so I'll leave it at that. If you have any questions, ask in the detail section, one at a time, and I'll try to answer those. My name is John Gabriel. This is a New Calculus channel. Till next time, goodbye.